Thank you. Good afternoon, everybody.
Afternoon.
So I imagine that most of you know what a light curve looks like when two stars pass in front of each other. I also imagine that you probably know what a light curve looks like if a star has some surface brightness distribution, star spots, faculae, and that star rotates. So they come into an outer view, and you get a nice periodic signal. But here what I'm showing is a month of data now phase folded on a 12-hour period. You can see it's nice and periodic. Okay, so you probably know about eclipsing binaries and rotating stars. I'm not as sure whether you know about this kind of star. So these things, at first glance, they look kind of like a mess. But if you look closely, if you phase fold, in this case on an 18-hour period, they're coherent. Okay, in this case, every 18 hours, this star shows 5 or so local minimum. So quick show of hands, who here knew that stars like this existed? If you do, please raise your hand. Okay, I see a few. Many of you don't. Now you know. What I want to talk about today is why I think they exist, and also why now might be a good time to think about. So these complex periodic variables are rare, but increasingly less so. We now know 100 objects like this. Originally, they were found by folks over at IPAC, Louisa Ribble, John Stafford, within the K2 era. Now, we're able to find lots of them using tests from space. So these are 25 new ones that I recently put out in a catalog. Here's another 25. And I don't want to belabor the properties of any one of these, just to reemphasize, they're all periodic, right? This isn't some little slice. This is a month of data for each of them. I'd like to briefly call out this one up here by the Zoom screen share icon. TIC 1411 has a kind of funny shape, really short period, 4 hours. We're going to return to that object later. What I want to talk about now is big picture. What are some of the broad population level properties that we see for these objects? And how might those connect with the physical explanation for what's happening? So the complex periodic variables are almost always short period. They have ages below about 200 million years, and they're all M dwarfs. Masses below about 40% sun. So that's important for a couple of reasons. It has connections to stellar astrophysics. It also has connections to exoplanetary science. Planets are common around stars with this mass range. The phenomenon that we see isn't particularly common, but we're not yet sure whether or not that's an intrinsic effect or just an observational bias. In other words, we see transiting planets around about 1% of stars. We similarly see this complex periodic variable phenomenon about 1% of M dwarfs. If there's a line of sight viewing requirement to see the phenomenon edge on, then the intrinsic abundance of stars that do this could be about 10% of M dwarfs below a couple 100 million years. Two other important observational points. The first is that the light curves are chromatic. So we see deeper features in blue wavelengths than we do in the red. And then the other kind of important and puzzling point is that there's no evidence for disks in any of these systems. Okay, so they're young-ish stars, but from, say, the infrared excess method or looking for spectroscopic accretion diagnostics, no disks. So the picture that's kind of been proposed for a while now in this field, that's been really hard to confirm, I might add, is that we have co-rotating clumps of circumstellar material that are moving around with the star. So presumably these clumps of material are somehow related to the star's magnetic field. The star rotates, the field lines rotate too, and thread this material. So that kind of brings me to my unwieldy title, transient co-rotating gas clumps around adolescent low mass stars. I thought about this picture for a while, And I basically agree with it. But what I'm saying today is that we're able to say a little bit more about actually confirming this picture and being more precise with what it is that we're seeing. Okay, when I say gas, what I mean is partially ionized plasma. And if there are circumstellar clumps of partially ionized plasma, we might be able to see it spectroscopically. Okay? I'll get to the spectra. It's kind of the punchline. I want to talk a little bit first about some of the other observational evidence that supports this picture. Okay, so the first line of evidence is really the photometry. So what I'm going to show here is half a year of data for one of these objects, LP12502, if you're interested in the name. What we see in the photometry is that these signals are periodic, in this case within an 18-hour period, but over time, the dips evolve. So what I'll do, I'll play this movie, and over here, one dip disappeared, while for the next couple months, these three will just stick around. So the dip disappearances turn out to be often associated with stellar flares. Okay, and that's important because we know that stellar flaring corresponds to a change in the magnetic field structure of the star. So if you have some magnetic reconnection event, that may be material that's moving around and magnetically trapped becomes free to flow outward or to go back onto the star. Of course, like I said, this is kind of wishy-washy. It'd be better if we could directly detect this circumstellar material that I'm saying should be there. So what we recently did was we got half a night of observations from Keck Science. And we looked at this one that I called out earlier, tick 1411. We selected this thing because of the really short 4-hour period. So this is the simultaneous light curve. And what I'm showing here in the middle is H alpha. And this is going to be a movie again. We have 5 hours of data. We sampled every 10 or so minutes. And what we saw in H alpha here is that the line split into 3, joined together again, split again, and joined together. Okay, the time dynamic spectrum on this far side shows you what's happening. This is chromospheric emission from the star in the center. And then out here, 300 to 500 kilometers per second. So anything like 3 to 4 times the star's equatorial velocity, we have emission from these plasma clumps, right? This is basically a confirmation that they need to be there. Okay, that's awesome. How did they get there? We don't know. Okay, we have a few ideas, but if you have ideas, I would like to talk with you. Basically, there are 3 possible origin stories for this circumstellar material that we now have. It either comes from the star, it comes from an old and undetected disk, or it comes from some sort of rocky body, like a planetesimal or even a planet. In any of these scenarios, I think what we're learning in these systems is astrophysically pretty surprising. Nobody predicted that this should happen, that these long-lived clumps, they last for months, I remind you, would be there. What exactly would we learn? Well, if it's the star, then we're learning that some M dwarfs can generate circumstellar plasma torque. If it's the disk, I'll remind you that these objects live out to hundreds of millions of years. So we'd be learning something pretty important about the time scale of disk dispersal around some M dwarfs. It would be much longer than most people expect. And if it's a planet, well, we're learning something about planet evolution that's basically analogous to the Jupiter Io plasma torques. So I'd like to go ahead and just summarize what I think the main points are from what we know right now, and maybe where this whole subfield is going to go. So the first point is that the complex periodic variables are observationally rare, but intrinsically, especially if a geometric correction is applicable, they might not be that rare. Okay, the second point is that the data that we now have, the photometry, but especially the spectroscopy from Keck, which I talked about today, also from Palomar, which I didn't talk about, but if you're interested, you can ask about. The data that we have require co-rotating circumstellar material. What I've been able to show is that it includes plasma. It might actually be a dusty plasma as well, That's one possibly interesting future direction to look into. For now, we know that it includes gas. And finally, just to wrap up, while I've outlined these three different origin stories, I want to emphasize that we're still in I think, part of this field, an era for this field, where the code has yet to be cracked. And so that means that there's plenty of room for new discovery in this area. Thank you.